Good morning. Today we can talk about the dynamic magnification factor. To talk about this value, we remember the case seen in the precedent video. We study a single degree of freedom system with an applied force the tip harmonic. So the loading is an harmonic loading. So there is a mass M with a force PT and a spring attached a spring with value K, stiffness K attached over mass, and damping force with coefficient damping for coefficient C. For using the second Newton law of motion, we can write inertia force plus the damping force plus the spring force is equal of applied force PT. So the inertia force is equal mass for acceleration, the damping force is equal or damping coefficient for the velocity, and the spring force is equal of stiffening for spring for the displacement. So we can write the second equation, differential equation. In the case of damped system, we can rewrite this equation in this way. Okay, in this way, formula 5, so the mass for acceleration plus the damping coefficient for the velocity plus the spring, the stiffness of spring for the displacement is equal of P0 for sin the omega bar for T. So where remember omega is the natural frequency, while rising of K divided for M. Psi, the damping ratio, is equal of the damping coefficient divided for 2 mass for omega. We can solve the particular integral with calculate the coefficient G1 and G2 in function of initial displacement and the velocity, and we can write this equation. And an example of movement of this equation we can see this blue line with a combination of transient response plus the steady state response. This equation is very important for the analyst, and the resultant rho of 2 vector represent the amplitude of steady state. So this value, this result value rho is equal of P0, amplitude of force, divided for K is the stiffness of spring. All multiply for 1 divided over racine of this 2 quantity elevate the 2. And the phase angle between these two vectors and theta is the equal of inverse of tangent of 2 psi for beta divided 1 less beta elevated 2. We can write in this way tangent of theta is equal of argument of inverse of tangent, and we can remember that in a right angle triangle the tangent is the opposite side of an adjacent side. So the opposite side is equal of numerator of this rapport, so 2 psi for beta. The adjacent side is equal to 1 less beta elevated 2. For the Pythagorean theorem, the hypotenuse is equal of racine of this 2 quantity elevate sum of this quantity elevate 2. We can now find the sine and the cosine of theta is equal of upside divided of the hypotenuse. Coseno di theta is adjacent side divided over hypotenuse. The stated response we can remember is equal of equation 12, and we can look the denominator in this equation is not n square root, but mean is the curve of the hypotenuse we find in precedent step. We can find the equation, can factor the equation 2 in this way. So xt is equal of this quantity where is rho, where is rho is, remember, is the equation 9 for this other quantity. Notice that the fraction inside the bracket perfectly matches with the definition of coseno di theta, the seno di theta in the equation, in this equation. So we can write all in the xt equal a rho for coseno di theta for seno di omega bar for t meno seno di theta coseno di omega bar for t. We can rearranging the factor internally, and we can see the expression in the bracket, in the square bracket, is equal of seno di alpha meno beta. In this case, alpha is omega bar for t, and the beta is equal a theta. So we can write finally the xt, the proximity is equal to rho for seno di omega bar per t meno theta, less theta. The ratio of resultant response amplitude to the static dispersion we will produce by the force P0 is called Dynamic Magnification Factor. So it's equal to rho divided for the amplitude divided for k. It is equal of this value. This magnificent factor we can plotting using Python in function of xi and the beta. So we obtain the curve in this way, where in x there is the frequency ratio beta, and here there is the plot of curve for different xi. For different xi. What can say about this curve? We can see that there is a decrease in amplitude of displacement with increase is in damping. It is maximum for 0% damping. And second observation, for frequency ratio equal a 1, that is a resonance, so the plasma amplitude become maximum. We arrive to infinite, and for beta and xi psi different of 0, d is very high. For frequency ratio near 1, the factor is very sensitive to damping. It can be very large depending upon of damping. And for consideration, for frequency ratio less 1, very less of 1, the factor is light more than 1 and appear to be independent of damping. For frequency ratio greater than 1, more bigger of 1, the factor tend to 0 and is essentially independent of damping depth. This information is very useful while designing machine foundation or structure against undesirable clear vibration. We can also plot the similarly the variation of phase angle with the frequency of ratio with the same value of psi, so psi 0.01, psi equal at 0.1 and psi equal at 0.2 and 0.1. And we can see that for frequency ratio less than 1, more or less of 1, the phase angle is close to 0. And the displacement is in phase with the force. For frequency ratio greater than 1, more of 1, the phase angle is very close to 118 degree, and the displacement is out of the phase with the force. The force and the displacement are in opposite direction. For frequency ratio equal at 1, the phase angle is 90 degree irrespective of damping. The displacement attained is peak when the force pass through 0. Okay, we can see also the Python code used to plot this equation. So it's a simple code where is write the equation we can plot, and we put the psi in array where you plot the different value, and the value of beta is change between 0 and 4. And here we can plot the value of in the graph we can see in present. This plotting we can find in in annex we want plot for different value, example of xi or for beta. Okay, it's all. Thank you. Bye.